Hello and namaste to the new video of Learn with Us. In this particular video, we'll discuss about the solving the ordinary differential equation, especially by using the Laplace transform. And before solving the ODEs by using the Laplace transform, I will try first solving the ODEs problem without using the Laplace transform also. So this video will be the revision for you for the Laplace transform, the revision of the inverse Laplace transform, the revision of solving the ordinary differential equation, especially the second order ordinary differential equation and the non-homogeneous one, and the revision of using the partial fraction method to solve the inverse Laplace problem. Okay, so I have put one of the example, question number 8, that is the second order equation, second order ordinary differential equation. I'll first try solving this equation without using the Laplace transform, and I'll come later solving the same problem by using the Laplace transform also. Okay, let's start without using the Laplace transform. Our problem is, our ODEs is y double prime, that means the second order of y, minus 3 times first derivative of y minus 10y is equals to 2, and the boundary conditions are given, and here the boundary conditions are the initial value of y, that means y at 0 is 1, and the y prime at 0 is given as 2. Okay, these are the boundary condition that will be especially used to get the value of constant of the homogeneous solution. Okay, if you notice this ODE, is or this ordinary differential equation is second order, and this is linear, and non-homogeneous, right? Since there is the forcing term in the right side, we said is the non-homogeneous. And if you have remember your ODE chapter, then you may know that the solution of second order linear non-homogeneous ordinary differential equation is the superposition of the homogeneous solution and the particular solution, right? Homogeneous solution and the particular solution. So we'll first determine our homogeneous solution, then we'll go to the particular solution. So for the homogeneous solution, let's take the homogeneous form of ODEs. That will be y double prime minus 3y prime minus 10y is equals to 0. This is for homogeneous solution. This is for homogeneous solution. So we can assume our homogeneous solution is exponential st. Our y prime will be s exponential st. Our y double prime will be s square exponential st, and putting all this value in this homogeneous ODE, we can get s square exponential minus st minus 3s exponential st minus 10 exponential st is equals to 0. S square minus 3s minus 10 exponential st equals to 0. Since this exponential st cannot be 0, because we are not looking for the trivial solution, we are looking for non-trivial solution, and this cannot be equals to 0. So what is 0? This whole term is 0. S square minus 3s minus 10 is equals to 0, and this is also called as the characteristic equation while solving the ODEs. Okay, and if you get the root of this quadratic equation, let's say is algebraic equation, you will end up with getting the factor x minus 5 and s plus 2 equals to 0. That will give s equals to 5, and that will give s equals to minus 2. And since you have the two non-repeated roots, let's say two unequal real roots, your solution will be y of t, that is the homogeneous solution, will be c1 exponential, the superposition of the two base term, right? The superposition of the two base term, exponential 5t plus c2 exponential minus 2t. We will later determine the value of c1 and c2 by using the boundary condition, but before that we need to get the whole solution. Okay, the whole solution is the combination of homogeneous and the particular solution. We have already obtained our homogeneous solution. Now it's time for the particular solution. So for the particular solution, since we have the some standard forcing function that is just a constant, and since this is just a constant, you can use the method of undetermined coefficient for the simple function like constant, either that may be the polynomial function or that may be the sinusoidal function, cosine function, or that can be like exponential function. You can use the method of undetermined coefficient. And by using the method of undetermined coefficient, what you can say is, if the forcing term is just a constant, you can assume the solution is a constant. You can assume the particular solution is a constant. And if the particular solution is constant, y prime is 0, y double prime is 0, and if you put everything in your equation, then what you can get, you will get 0 minus 0 minus 10 times a is equals to 2. That will end up me with a equals to 1 by 5. So my final solution, okay, the general solution is c1 exponential 5t plus c2 exponential minus 2t negative 1 over 5, right? This is my final solution, but still I have to use the boundary condition to get the exact solution. This is the general solution. I need to get the exact solution also. So to get the exact solution, now what I will use, I will use my boundary condition. And for the boundary condition, I already have y of 0 is 1 and y prime of 0 is 2. So y of 0, let's calculate our y prime first. Y prime t is equals to c1 5 exponential 5t plus c2 minus 2 exponential minus 2t, and this will be 0. Okay, so I can simplify these two. 5c1 exponential 5t minus 2c2 exponential minus 2t. Now let's take these two boundary condition. If I took y at 0 is 1, then my 1, and in this whole solution, my 1 is equals to c1 exponential 0 plus c2 exponential 0 minus 1 by 5. That will give me c1 plus c2 equals to 6 by 5. I have one equation. I still need to get one more equation that I can get from this boundary condition. Okay, y prime 0 equals to 2. So y prime 0 equals to 2. That means 2 equals to, if I put in this equation, 5c1 is 0 minus 2c2 is 0. Okay, this will be 2 times 5c1 minus 2c2. So you have two equations. You can use either the elimination method, or you can use either the substitution method, any method, and calculate the value of c1 and c2. So let me take the elimination method. I will multiply this by 2 and just add both of them. I will come with 5 7 c1 equals to 12 by 5 plus 2. That will be my 22 over 5. That means my c1 will be 22 over 35. Similarly, I can calculate my c2. My c2 will be 6 over 5, 22 over 35. That will be 42 minus 22 over 35, 20 over 35. That can be simplified to 4 over 7. So my exact solution, y of t, is, my c1 is 22 over 35. You can see here for exact solution, this here exponential 5t plus 4 over 7 exponential minus 2t and 1 over 5. And this is how I solved my ODEs without using the Laplace transform. So this is my solution. Let me check here. I think this resembles the options 1, right? 1 over 5 plus 22 over 25 e power 5t plus 4 by 7 e power minus 2t. Okay, this is the method of solving ODEs. Now I will use my Laplace transform to solve the same ODEs. Okay, the same ODEs is y double prime. Okay, let me check. Minus 3y prime minus 10y is equals to 2. Y of 0 is equals to 1 and y prime of 0 is equals to 2. Here If you remember your Laplace transform again, so if the Laplace transform of y, if the Laplace transform of y is ys, here small y, the small letter y denotes the time domain and the capital letter Y denotes always the S domain. In Laplace transform, this is the standard form. We write the capital letter is the S domain and the small letter function for the time domain. Okay, so the Laplace transform of first derivative of y will be s capital Ys minus small y at 0. Okay, this small y at 0 means the initial condition. This is the initial condition, that means the function of yt at t equals to 0, and this is the Laplace form. So the next is, you can get double prime y is s square ys minus s y0. Sorry, let me check here. Okay, s y0 minus y prime 0. This is for the second derivative. Okay, and these formulas are important if you have to solve the ODEs by using the Laplace transform. So now I will get back my ODEs. This is the given ODEs. They are the initial condition. What I will do is, I will first convert this ODE into the algebraic equation. That's the main application of Laplace transform. I will first convert the ODEs into the algebraic equation, or let's say the polynomial equation. Once I convert it to the polynomial equation, they can be solved. And once I get the solution in the S domain, I'll get the solution back in the time domain also. Okay, let me show. This is the ODE. Okay, this is the ODE. Now by using the Laplace transform on the both side, I can write Laplace transform of this left side, 3y prime minus 10y is equal to Laplace transform of 2. So this can be written as Laplace transform of y double derivative minus 3 times Laplace transform of y derivative minus 10 times Laplace transform of y equals to the Laplace transform of 2 is nothing but 2ys, right? So the Laplace transform of y double prime is s square. You can review here, s square ys minus s small y0 minus y prime 0. So this is written with this 3 term. Now the time for this Laplace transform of first derivative, this can be written as s ys minus y of 0, and the third one is 10 ys. In the right side you have 2ys. Now you can put the value of your boundary condition, that is y0 y prime 0. You already have this value, so I can write s square ys minus, this is 1, so minus s, this is 2, right? You can see here, this and this. So this is my 2 minus 3s ys plus 3 minus 10 ys equals to 2ys. And you can see now your ODE has been converted into the algebraic equation, or let's say the polynomial equation. Okay, and they can be solved now. They can be easily solved to get a solution of ys. So now I will get the solution of ys. This is algebraic equation. I will get the solution of ys. Let's take ys common. You will have s square minus 3s minus 10. In the right side you can have 2ys. You can have plus es and minus 1. This can be written as a 2 plus s square minus s divided by s. So if you see, this s square minus 3s minus 10 can be factorized. This can be factorized and written as s minus 5s plus 2, right? Okay, and the right side you have 2 plus s square minus s divided by s. So my ys, the solution y in the s domain, okay, in the s domain will be 2 plus s square minus s over s 5 s plus 2. Now the last task you have to do is the get y in t domain, get your y in t domain, and to get the y in t domain, what you need to do, you need to just get the Laplace Laplace inverse. You need to just get the Laplace inverse of this function, this ys. So now your yt will be Laplace transform of, sorry, Laplace inverse of ys. That means Laplace inverse of 2 plus s square minus s over s minus 5 s plus 2. And to get the Laplace inverse of this term, the easiest one is to get the use of partial fraction. If you use the method of partial fraction, since you can see here the numerator has the degree 2, the denominator has the degree 3, right? And in the denominator you have the 3 linear factor. That means you can use the method of partial fraction. You can write this is equals to a over s plus b over s minus 5 plus c over s plus 2. Okay, let's see this yt. We'll come back to this equation again, but before that let's find the value of abc first. So to get the value of abc, we can write this as s minus 5 s plus 2 is equals to a over s plus b over s minus 5 plus c over s plus 2. So we can multiply these whole terms on the both side. That will be a s minus 5 s plus 2 plus b s plus 2 plus c s minus 5. So to get the value of a, b, c efficiently, you can take some smart values of s. Let's take s equals to, if s equals to 5, then we have 2 plus, we have learned the method of partial fraction in our previous two videos, the part 1 and the part 2 video. You can review that from there also. So here 2 plus 5 square minus 5 is equals to, this will be my 0, this will be my b times 5 times 7, this will be my 0. So my b will be 25 minus 5, 20, 22 by 35. Okay, my b is 22 over 35. Now let's take if s equals to minus 2. Okay, 2 plus minus 2 square minus minus 2, that will be, this will be 0, the first term, the second term will also be 0, the third will be c minus 2 minus 7. So this will end up with 4 minus 4 plus 2, that's the 8, equals to 14c. That means c will be my 4 by 7. Now to get the value of a, I can suppose s is equals to 0, 2 plus 0 minus 0, this will be a minus 5, 2, the other will be 0 and 0. That means a will be negative 1 over 5. So these are my a, b, c value. So my yt will be now, Laplace inverse of, that means my a is negative 1 by 5 into 1 by s, plus next is b over s minus 5, my b is 22 over 35, 1 over s minus 5, and c over s plus 2, right? So I can write this is minus 1 over 5 Laplace inverse of 1 over s plus 22 over 35 Laplace inverse of 1 over s minus 5 plus 4 by 7 Laplace inverse of 1 over s plus 2. Now you can get the Laplace inverse of all the terms very easily. This will be 1, this will be 1, so minus 1 over 5 plus the Laplace transform of this term will be exponential 5t. The Laplace transform of this term will be exponential minus 2t. So my final solution is (4 by 7 exponential 2t). And this is the same solution that we have obtained without using the Laplace transform. This is the one we have obtained without using the Laplace transform, and they are similar result. Okay, same result there. These are the solution. So we'll start here for the application of Laplace transform to solve the ODEs. We'll come with a more mathematics review in the next video. Until then, stay tuned. Thank you very much.